Hello. So what you see on the screen here is a family of Poncelet family of pentagons, blue, inscribed in a circle, and circumscribing a special caustic, this brown thing here, uh, for which one of its foci coincides with the center of the outer circle. Now, I would like to refer to a paper by professors Richard Schwartz and Sergei Tabachnikov from 2016, uh, published on Mathematical Intelligencer 2016, and the title, and I'll leave a link in the description, titled Centers of Mass of Poncelet Polygons 200 Years After. So amongst several interesting theorems, one that is proved there is that for a generic Poncelet family between two generic conics that close a family of n-gons, the locus of C0, the vertex centroid, and of C2, the area centroid of such polygons, will always in fact, sweep ellipses or conics, modulo the degenerate cases where they might be points. And simultaneously, they prove that the locus of C1, the perimeter centroid, and what is a perimeter centroid? Is if you can compute it by calculating the center of each one of the sidelines of a polygon, and then computing a weighted average, where the weights are the lengths, are the side lengths themselves, right? So you get this third centroid called the perimeter centroid, represented here as C1. And what they say is that in general, C1 will not sweep a conic. Now, for this specific family, which I sometimes call MacBeath family, after the MacBeath inconic in the n equals 3 case, okay, has the following degenerate behaviors. Number one, the vertex centroid C0 is stationary, as is the area centroid C2, and both of them lie on the major axis of the caustic. Secondly, and I'll show a few other n-gon examples here, the locus of the perimeter centroid, which in general is not a conic, is a conic here. This is a numerical ellipse with a major axis coinciding with the major axis of the family caustic. So we thought this was pretty cool. Let's look at some other examples here. For example, n equals 4. We got the same kind of situation. Vertex centroid C0 and area centroid C2 are stationary on the major axis, with this being a special case for which the vertex centroid C0 coincides with the center of the n equals 4 caustic. C1 continues to sweep a beautiful ellipse, which is major axis aligned with the major axis of the caustic. How about n equals 3? For which we have a proper MacBeath inellipse, right? The MacBeath inellipse of a triangle is one for which one of its foci coincides with the circumcenter, and the other focus is its isogonal conjugate, its fixed orthocenter. So this point here is a fixed orthocenter of this family. But for this n equals 3 family, you get, first of all, a well-known fact for triangles that the vertex and area centroids coincide. This is only true for n equals 3. And you can see that they are also stationary, as before, whereas C1 continues to sweep this beautiful ellipse. And then for n equals 3, might be able to actually derive this. Perhaps for n equals 3 and 4, we might be able to derive the parameters of this particular ellipse here. Okay? So that's n equals 3 for you. Just repeating, we go to n equals 4. And now C0 is at the center of the caustic, and I can change the eccentricity of the caustic, and I get different phenomena. One thing that you notice is that the higher the eccentricity of the caustic, the larger or the more visible the locus of C1 becomes, right? And then for n equals 5, just to finish, you get that phenomenon again. Let's take a look at n equals 6, just to check. you can see here that C0 and C2 continue to appear stationary, and I've checked this numerically, they are stationary. And then C1 continues to sweep. Let's increase that eccentricity without exploding the numerics. Continues to sweep what looks to be an ellipse. Here the two foci. Okay, so this seems to be extending for all n. For the case of the MacBeath Poncelet family. And I'm just going to leave you guys with this animation of n equals 5 for a few seconds. And I'll see you on the next video. Thank you.